Greetings, I'm Yvonne Stapp for Science for the Public, and I welcome you to today's Contemporary Science Issues and Innovations program. This April, there was an exciting announcement from the Illinois Fermi National Accelerator Laboratory, better known as Fermilab. The news was about the first run at Fermilab of the Muon G2 experiment. And if that leaves you puzzled, hold on. We're about to hear what it is and why particle physicists are hoping this is a breakthrough they've been anticipating for years. If confirmed, it will be the most important event since the confirmation of the Higgs boson about a decade ago. Our two guests are Fermilab physicists who together will explain, one, how subatomic particles reveal the structure of the universe, and two, why it's necessary to collide subatomic particles at nearly the speed of light to get such information. Dr. Steve Nahn is a senior scientist at Fermilab and US project manager for the CMS detector upgrades at the Large Hadron Collider at CERN in Europe. Dr. James Mott is a Wilson Fellow at Fermilab and adjunct assistant professor of physics at Boston University. And he was involved in developing the special electronics for the Fermilab Muon G2 experiment. Gentlemen, welcome and thank you very much for joining us today.
It's absolutely my pleasure to join you.
Okay, and I'm going to ask to start with just a little bit of background from both of you about subatomic particles. First of all, what are subatomic particles and how does this connect with the standard model?
Okay, so we don't have a way to negotiate, so I'm just going to jump in, and then
sure.
at some point,
both of you in this.
I'll make a difficult transition, and then James has to explain the hard things. So subatomic particles are what make up all of the particles we know about that make up, nature and the world and the universe and everything, right? It's the smallest building block. You can take subatomic particles called quarks, and you could build protons and neutrons, and then you can make nuclei out of them. And then you can take a subatomic particle called the electron, and that can orbit it and make an atom, and then atoms make molecules, molecules make cells, cells make us. So that's kind of how it works. But there's a whole family of more esoteric subatomic particles. Actually, there's only 12 total, really. So there's not that many hard. It's not like the periodic table where you have to keep track of 120 elements and more so, right? It's only 12, so it's not that hard. And they come in sort of three families. So there's, the first family of quarks are the up and down quarks, and they're sort of coupled with the first family of leptons. Quarks interact with a strong interaction, leptons do not. So there's electron and neutrino, the electron flavored neutrino. But then there's this second family, and that's where James comes in, because he's using a member of the second family, the muon, to probe some very, very important and very precise physics. So there's a second family and a third family. And then all of these things interact through what we call either weak interactions or strong interactions or electromagnetic interactions. And that's how you build the universe.
Okay, now all of this stuff goes to the standard model, all this very basic stuff, but apparently there is material information missing still, and that's why you continue to do these kinds of experiments. So how do physicists, James, know that the standard model is incomplete?
Right, well, so the standard model is it's a very successful theory, right? It's one of our most successful theories, and that's almost to our frustration, right? So it came around in the late 60s, it kind of built up, and it got to the point where now it just makes these predictions, and we do the experiment, and it matches up well. Right. And then we do another experiment, and it matches up well, and we keep digging further and further and trying to beat this thing, and it keeps working. But we know that it's fundamentally flawed in that it doesn't do things like, it doesn't incorporate gravity, for example. And we all know gravity exists, right? So there's something that's missing. And it has some other problems as well, right? It doesn't have a good explanation for dark matter, for example. So we know that there's dark matter in the universe from how galaxies spin and from observing that gravitational interaction. But the standard model doesn't provide a good candidate for what that dark matter might be. There's other problems in cosmology as well with things like dark energy, and we don't know what that is either. And then really fundamentally as well, the standard model doesn't explain why we're here at all, right? So in the Big Bang, we anticipated we should have made matter and antimatter in about equal proportions. And then something has to be in there to just tip the balance, which is why we're all made of matter and why we're not all made of antimatter. And yet at the moment, there isn't enough of this asymmetry in the standard model to explain that. So they're the kind of things that we're looking for. There must be something beyond the standard model. And what we've been trying to do for many, many years is just chip away at it and find what is that next thing beyond the standard model.
Right. So there's this incompleteness, and they've been working at it. And you pointed out that you have to do these experiments and refine these experiments over a period of time. So I'm going to switch to ask Steve now about the CMS and the CERN accelerator to find out what goes on there. Just a general idea of the systems there, if you would, Steve. And then we got to the Higgs through there, but now, and then we'll switch to the Fermilab and the Muon G2, if that's okay.
That sounds good. I think, so there's a very nice way that we kind of divide up the ways we search for physics beyond the standard model, like James was talking about. And one you could, sort of call the shotgun approach, which is, a direct observation of something that's outside of those 12 particles that we haven't seen before. And the standard model, sometimes extensions to the standard model predict new particles. For instance, the Higgs itself was predicted 40 years before we actually demonstrated that it existed. Right. So that was sort of the first, if you like, extension to the standard model. People argue whether it's part or not part. It wasn't part, and then it became part because, well, we found it was part. So at CERN, that's what we do. We collide particles together, protons, which are a kind of hadron, at the very highest energy we can, because everybody knows Einstein's equation, E equals mc squared. So if you're trying to find a particle that has a heavy mass, m, you need a lot of E, energy. The higher energy you go, the further you probe in mass. And that's sort of the postulate for why we haven't seen these particles before, because they're so heavy that they don't get produced in nature. So we have to produce them themselves. So we crash protons together in a series of accelerators. Each one kind of gets it up to, 5th gear, and then 10th gear. The next one kicks it up to 20th gear, and they go around, and then eventually we collide at them in the middle of our detector. And our detector measures what comes out. And from what comes out, sometimes you can reconstruct particles and build new, what they decayed from. And okay, that must have been a Higgs, because look, there's a bunch of particles at the same mass. And in our little book, we don't have any particles at that mass. So that must be a new particle. Woo-hoo. Right? That's what we do at the LHC.
Right.
There's two sort of, okay, good. Sorry, is there questions? I'm going to go on for another minute, and then I will turn it over.
It's just get the background, and thank you for that. I think people are familiar with the CERN, with the Large Hadron Collider, but why these collisions are necessary. And then you have upgrades, and you have huge amounts of data. So there are two things I'd just like to check quickly there. That first of all, it will require upgrades with refinements of the technology, right, over years. And then the next thing I want to just check with you is about the data there too.
So there are sort of two ways that there's another aspect to how do you discover something. You make enough energy and you can reach higher mass. But it might be that the process is just so rare that it would take you 100 years at the current collision rate to produce one of those interactions that you're looking for. So what do? You increase the collision rate. And when you increase the collision rate, you start getting more and more particles. We're supposed to, we collide at like 40 megahertz. 400 million times a second, we have a collision. Did I get that right? Yeah, okay, right. So, and then the more intensity you put into each of those collisions, the more particles you put in the collisions, the more what we call the luminosity, which is essentially the flux, goes up. We have to upgrade our detectors to keep up with that flux, right? So that we can increase the amount of data we're collecting in a year by a factor of 100, but of course, our detectors have to be able to take all of that data faster. And that's what the upgrades are about. We went through one series of upgrades already, which we call phase one, sort of strategic upgrades for the next 3 years. And we're in the middle of preparing for another upgrade, which is called the high luminosity LHC upgrade. So in the next 3 years, we're supposed to increase our data set by a factor of 5 to 7. And then after that, we're supposed to increase the data set by about we're going up to, I think it's like 20 or more. I can't even remember. I'm like 3. I know the numbers, but I can't remember the midpoint. So, I think it's like a factor of 10 more over the next 10 years, say starting in 2027.
Right.
So we have to upgrade our detectors for that.
Yeah, and each time you can really refine, I guess, how much data and the quality of that data. Is that correct? And I guess I want to get clear that if it's a huge amount of data, like you see a lot of stuff, but you can't keep it all. Is that correct?
That is correct. That's how my version, this collider physics, especially when you collide hadrons, there's a lot of stuff that comes shooting out.
Yeah.
And more often than not, by factors of like 1 million, you're not interested in it. You're interested in that 1 in a million event. So you have to be very selective very quickly about what you keep based on sort of general things you can measure in orders timescale of a microsecond, right? And is this a keeper, or do I toss this one and wait for the next 1 in a million event to come by? And you want to make sure you grab the 1 in a million. And that's why you have to refine your detectors and make them very powerful so that you can handle all that data flowing through, and you can very selectively pick out the events you want to keep. And still, at the end, our data set will be, I don't even remember the comparisons anymore. It's like 1 billion times the OED or something like that. It's huge amounts of data that we're talking about.
Right. That's almost scary trying to write things, isn't it?
Yes.
But it's a huge challenge. And one more thing before we leave the CERN is that this is a huge international undertaking. Is that correct?
Oh, indeed. CERN it's a wonderful thing. It was started after World War II by Isidore Rabi, I think, who said we should have a place for science to come together and work for peace. Peacefully, scientists from all around the world. So I have about 3,000 collaborators or so myself from 183 different institutes and on the order of maybe 60 or 70 different countries that contribute just to my experiment. There are 3 other experiments around the ring. They have similar numbers and similar diversity of people coming to all come together for science. And they're all volunteers, kind of. So it's a pretty amazing thing, actually.
Yeah. Well, I've understood that people that in normal life who would be enemies have to put all that aside. And it's just a whole new approach. It just says this has, in many ways, replaced all these old primitive tendencies that we have, because you are focused on really learning something very deep. That's fabulous.
Yes, and there is a healthy competition among the experiments, but we also rely upon each other, because if my experiment makes some outrageous claim, there's another experiment, and if they don't make the same outrageous claim, then everybody's going to say, you guys, you goofed something up. You go reconnect your wires and try again, kind of, because then that's actually happened. So we cross-check each other.
Right. And on that experiment, I know that you have to really file through huge amounts of data, confirm things. It takes a very long time. And that brings us to the Muon G-2 experiment. And we will switch to James now to ask him about this experiment and why there is all this exciting. Dr. Mott, I need to start with asking you a little bit about Fermilab. I think that's a familiar name also, but just a little bit of background about what they do, and then this remarkable upgrade there that went with this experiment, if you would.
Yeah, sure. So Fermilab's kind of America's premier particle accelerator lab. Is kind of the tagline that we give ourselves. It's a big complex just outside of Chicago. And there's many accelerators there. So similar to what Steve was talking about with CERN and all the different accelerators that are chained together to crank particles to higher and higher energy. So we have the same sets of accelerators at Fermilab. So over the years, there's been many different experiments. Before the LHC turned on, the highest energy colliders in the world were at Fermilab. So they've had some great discoveries there. For example, the discovery of the top quark happened at Fermilab. And then since they've turned down and handed over that high energy mantle to the LHC, Fermilab's focused more on neutrino physics. So there's big neutrino experiments coming there. But we also do other things, like, for example, the muon physics that I'm working in. There's a big contingent who work on CMS analysis and CMS upgrades. So that's stuff at the LHC still, as well as, oh no, now I'm playing the game of naming everyone, I'm going to forget something. But yeah, it's like astrophysics and cosmology, there's theory, there's quantum science, a lot of accelerator research. See if I've missed anyone that I should have.
I think you did well.
Now it's on you too, you've forgotten as well. Okay, so yeah, so that's basically what we do. It's kind of, yeah, blue skies research, fundamental science, trying to answer these big questions.
And then this experiment, which is amazing, but it started out, I guess, in another lab, the Brookhaven, I believe, but in any case, would you now tell us about the Muon G-2?
Yeah, so to come back to something that Steve was alluding to earlier, right? There's sort of different ways that we can try and figure out what's wrong with the standard model. So Steve described the kind of high energy approach, the energy frontier, we call that, right? So that's just try and go to the highest possible energies and see something directly. But there's another approach, which is the experiment that I work on that we take. And what we try and do is measure something very, very precisely and just see some hint of something from a higher energy coming in and influencing this number. So the experiment I work on, it's called Muon G-2. And you're right, it ran previously at Brookhaven National Laboratory in Long Island in New York. And so what we do, we take these particles called muons. So they're in the second family of particles that we talked about earlier when we were introducing the standard model. And they're the counterpart to the electron. So it looks very similar to an electron. It behaves in a very similar way, with the exception that it's heavier, right? It's 200 times heavier. And so that means it's got extra energy. And so it decays, right? So it only lasts for 2 millionths of a second, and then it decays into an electron, right? So these muons, we take them, we can make them at the accelerator complex at Fermilab. We can make these muons. And what we do is we put them in a big magnet, and we measure how they wobble inside this magnet, right? So they have a property called spin, right? It's just a fundamental property of these particles. You could think of it like a bar magnet, something like that. So it's just like an arrow that points in a given direction. And if you put that inside a magnetic field, then it starts to precess, right? Like a spinning top would precess, or like the beam on a lighthouse, right? It's just going to go round and around and around inside this magnetic field. And what we measure in our experiment is the frequency, or so the speed of rotation of this spin, right? So that's what we measure. And we measure that very precisely. And it's also a number that we can use the standard model as input, and we can calculate the same number very precisely. And if they match up, all's well with the standard model. But if they're different, it means that in our measurement, we're seeing something which isn't in the theory, right? So there's something in nature which is not in our theory, and it's then pointing to maybe something that's different. Yeah. So the experiment, it ran in Brookhaven around the turn of the millennium, right? Kind of 99, 2000, 2001. And they did this experiment, and they noticed that there was a difference of kind of 3.5 standard deviations. It's like, that's very unlikely, right? It's less than 1 in 1,000 chance that would just happen. But you kind of do these things and you think, well, before we start saying we've seen new physics, was there a mistake in the experiment, right? So this is again what Steve was talking about. You need another experiment to try and confirm it. And that's what this experiment at Fermilab set out to do. So we've tried to repeat the experiment that they did at Brookhaven. We've changed all the people, we've changed all the detectors, we've changed the beam, we've changed as much as we could easily change, and we rerun the experiment. And then when we had our result come out in April, we found that we got the same number as them, right? We agree with the Brookhaven one and not with the theoretical prediction. And so now that means that when we combine those two, we're up to now 4.2 standard deviations different between the experiment and the prediction from the theory. So that's probably telling us that the experiment's okay, right? It probably wasn't an experimental mistake. And so now it's like, well, is the theory number right, or is it really new physics? So people are working hard on checking the theory. They have been for decades. It seems to be holding up. So we're all getting excited that maybe this is a hint of some new physics that we're seeing.
Right. Dr. Mott, it takes a while to go through this to really confirm it, evidently, but will you do another run?
Yes, so the data that we released last April was from what we call run one. So it was from just 3.5 months of running in 2018. So we also ran in 2019, 2020, we're still running now, and we'll carry on running for 1 or 2 more years. So the actual amount of data that we've released here in this result is only 5% or 6% or so of our expected total. So it's just a very small fraction of what we're going to collect. But even then, it was the same precision that they were able to achieve at the Brookhaven experiment. So we're already there, and we're just scooping up more and more data, and we'll continue to release these results staggered, maybe 2 more sets of results. And I mean, it would be surprising now if the result was significantly different, right? The first one was always going to be the one that if it was going to be wildly different, it was much more likely to be the first one. But of course, we'll look, and our uncertainty will shrink down and down. And then what we're hoping is that we'll shrink down to the point where we're more than 5 standard deviations different from the theoretical prediction. I mean, that's just because historically we've used, that's the threshold for which we claim there's something really here. Because statistically it's vanishingly small, but also it's kind of, if you make a mistake, you have to make a really big mistake to get it 5 standard deviations wrong.
Wow, this is very exciting. I guess for physicists everywhere must be watching this, but for these results, do you have like an idea of when you will know? Like you could say,
Oh,
ha ha ha.
it's always a dangerous question.
Okay. It's just Monday. I thought I'd throw a little excitement.
Give it a shot, James.
No, I know that they say that, of course, people were not, physicists were not, particle physicists were not really surprised at that Higgs. It took a long time to just make sure that it was. And I remember back then that Dr. Nahn referred to it as Higgs-ish when he was on our program to explain when, that came through. But now it takes I want to just get across that it takes a long time to confirm these things. But in the end, if this does prove true, then what does it mean for physics and for the understanding of the universe?
Yeah, I guess I can take another. Well, so I mean, it's very exciting, right? It would mean that there is some new physics out there that's potentially within reach, right? So the worry, I think, for many particle physicists after the Higgs discovery was that there isn't like another guarantee that you're going to see anything.
Yeah,
right? A long way. It could be a huge energy scale before you see anything. Whereas this is kind of hinting that, maybe this thing is big, right? This discrepancy between what we're seeing in our measurement and the prediction is large. It's the same size of deviation that we see from the electroweak force, which is big. And so then the question becomes, well, why isn't it pouring out of the Large Hadron Collider, right? Why is new physics everywhere? But it means that it could just be around the corner. So there are maybe, I don't know, some people are getting excited as well that maybe there's some hints of the same sort of physics that's also coming out of the LHC at the moment. There are some anomalies in terms of how we look at these decays from, say, B mesons or D mesons, just how they decay into different particles. how the difference between the muon decays and the electron decays there, the standard model would say they should be the same, but they're slightly different. So there's now one experiment on its own, which is from LHCb, that's just like 3.3 standard deviations, right? So that's getting up there as an interesting result in itself. And so maybe these things are starting to interconnect, and maybe we're just turning the corner now and about to embark on a time where we'll figure out what this is, and then we'll be able to really study it.
I've understood, but this is from a physicist, and she wrote this in the recent article, her recent article in the New York Review of Books, that that this, if this is proven true, that it may indicate a fifth fundamental force, and it may indicate the existence of new subatomic particles. I take that. It might really shake up, she said, our understanding of nature. Would you agree with that?
Yeah, I mean, so there's many different explanations for it. So this is the problem with our experiment. It's very precise, and we get this. We can really look down and drill down and see this number, but it's just one number, right? So you compare these two numbers, and it's like, well, why are they different? And it's like you can come up with many, many, many different models which would explain why they're different. So yes, some of them are new forces, some of them are new particles, some and both. And there are many different ways of doing it. But what we really do know is that everything we put in the standard model right now, all the physics that we actually know, that can't explain it. So there's something that is new, and what it is, we don't know at this stage. And so we're going to need to then have other experiments that see similar anomalies. So that can either be in experiments at the kind of high intensity, high precision frontier like ours, or in the LHC, looking at different energies and higher luminosities. Right, we're going to need to try and tackle these from many different sides to try and figure out, like, all seeing these different anomalies and piece together the puzzle and say what we're really seeing.
I see. This is really an exciting time then, isn't it?
Yes, we're very.
It's what an era to be in this field, and I imagine that the technology is getting better and better all the time, so that you really expect to penetrate the secrets of the universe here in a very big way. In what, the next 10, 20 years, will you get really new insights?
Oh, I don't know. Who knows? Who knows?
Gotta be brave.
You gotta be. You guys are so cautious. Come on.
Well, I mean, so the funny thing is, I'm going to intercede here for a minute, James, because what you were just describing to me reminds me of how particle physics sort of started way back when. We described this very simple thing. There are 3 families. Each family has 4 constituents. So you get 12. Easy. But before the standard model, there was all sorts of conjectures about how some of those, we're discovering pieces and bits of that thing and trying to put them together into some sort of logical construct. And what James was just saying kind of reminds me of that. We are, now starting to find new pieces, and how does this fit to that other strange thing we see over there and that other strange thing over there? So we sort of have, come back to the beginning in trying to extend this really successful model, and are on the precipice of that. So, in that sense, I feel, I'm not sure confident. I mean, you were right. Physicists are always very conservative. We need 5 sigma. That's a big confirmation that, this is really different. And if we're at 3 sigma, we're like, maybe. So we are conservative about that. But on the other hand, I think, there are indications, as James said, coming from even different pieces that we might be able to find something. And yeah, if so, it's going to happen in the next 20 years.
Yes, right. Which
if not, we'll all be really sad.
I know you will.
20 years from now.
But the thing is that you're just at the right moment. It seems like you're right on like a breakthrough moment, possibly here, and it would maybe open up things, this area where so much as we don't understand very much of the universe, and this would really finally give you an opening to it. It sounds like I can say that, but you have to be cautious. So, but you expect to refine your instruments and these experiments, and you will make all these wonderful discoveries. Will this be ongoing at Fermilab too with the Muon G2? You're going to do more experiments there, or I know you're in the run now.
Yeah, so we're still taking data now for Muon G-2. So we'll collect up. So there will be small upgrades to the experiment, but nothing on the scale of the upgrade that Steve was mentioning earlier.
Right.
Our precision is just going to get better by seeing more and more muons. Right, we just need to have higher and higher statistical precision by seeing more things to get this number known precisely. But the muon physics is not done after G-2 at Fermilab. There's a new experiment that's coming on at the Muon campus that will switch after G-2 called Mu2E. And what that's looking for is a muon, which is just going to convert directly to an electron and a photon, right? So in the standard model, that doesn't happen, or it happens with a vanishingly small probability. So actually, the fact that it happens at all means that means there isn't some fundamental thing that means that can never happen. It means it happens, and we don't understand why it's happening at such a low rate that we can't see it. So that's following on a series of experiments that have tried to push that. They've searched for that for many, many years. But this new experiment is going to take a big chunk and a big leap forward and go a factor of 10,000 times better than the current limit. And really have a look. And so that's potentially another avenue where we could see something. Anything we see there is new physics, right? If you see something when that experiment switches on. And there are, again, other models that people are building that say you can explain these things at the LHC, you can explain G-2, and you would predict a big signal for Mu2E, for example, right? And so who knows, right? When that experiment turns on, if that sees something beyond the standard model too, then that's very exciting as well.
Well, it's a great time for physics. I really appreciate all this information. And I'd like to add that it's a great time for the general public too. This is really difficult information, but the projects are more open to the public. More of the information is more available to the public, and people like you who can explain it for us, because it's quite a hard, challenging information. But gentlemen, thank you ever so much for joining us today. I wish you the very best in your careers, and thank you for your contributions to science to Dr. Steve Nahn and Dr. James Mott. Thank you.
Thank you for having us.